Okay, good afternoon, everybody. I hope Barry's having a wonderful day. So before I say anything, I want to note that assignment 5 is out, so this is the final assignment in the course. I've given you a couple of extra days from the date that is scheduled in the course outline. This is to ensure that you can complete the final problem with sufficient amount of time. I just thought it would be fair to do so. And it gives you a little bit of extra time. I know that as the term sort of wraps up a little bit, I know that there's other courses with other assignments in there, and I just want to be nice to everybody. So, that being said, just take a look at it. I recommend just doing it in pieces, because a lot of this will be like, where I do a lecture, then you can work on the next problem. I do a lecture, you can do the next problem. For example, the first problem involves applying the greedy algorithm I showed you last class. So, anyways, let's talk about what we're going to do today. So today we're going to be talking about how we can analyze recursive algorithms. So I'm working up to an algorithm design technique called divide and conquer, which you've actually seen before in 210. So a lot of this is just me building on top of your intuition about recursion and how you might analyze recursive algorithms. So I'm going to be providing you a variety of tools and concepts that are going to be very helpful for doing this. So by the end of my discussion with you at this, either today or next class, you'll be able to easily analyze algorithms that have running times that look something like this recurrence relation. Or these are constants, like the a, b, the d, and we have some function f. So many running times for recursive algorithms take a form that looks like this. Not all of them, but many do. Many that specifically are so-called divide and conquer algorithms do. So we'll see this later on, like I said, either today or on Tuesday. So there's going to be 3 main methods I'm going to focus on. So I'm going to be highlighting 3 of them. One of them I'm going to get you to read in the notes, but I assure you that I give lots of examples, the so-called master theorem. I recommend that you only look at it after you look at the simple master theorem, which we might have time to talk about today. We'll see. And of course, we'll start talking about recursion trees, which are very closely related to iterative substitution or repeated substitution. They're synonyms for the sake of this discussion. So I'm going to talk about a couple of things that we're going to kind of need to build up some of the theory I would like to use so that I can invoke some of the nice properties I want to use. Some of these things are something you can easily apply in settings that have nothing to do with recursive algorithms. Just to be very clear, I like to show these to students so that they get some familiarity with a couple little neat tricks you can do with analysis that you may not have noticed before, or they're just sort of subtle assumptions you may have made in previous courses that some profs might have done, and they never really explained why they're able to do this. So I thought I would just show you a couple of fun techniques or properties that functions, in particular complexity functions, typically have. So the first one is I want to talk about the so-called concept of an eventually non-decreasing function. Sometimes this is called asymptotically non-decreasing. So this is simply a function where there exists a constant n0, akin to the definition of big O, quite similar, right? It has a positive integer constant n0, such that for all values of n, after and including n0, it has to be that the function, if I give you n, it has to be less than or equal to the function when I give you n plus 1. So you might ask, what does that look like if I plot out what that function looks like? So you may have heard of some of these terms back maybe in your calculus days, but I thought I would just remind you of them. So for example, if I have a function that's plotted out like this, so a function like a quadratic, for example, on at least the domain that we're talking about, this would be something you would call an increasing function, at least from the context of a complexity function. Now, notice here that it's just because every time I put in one number, when I put the next highest number in as the input, it always gets bigger. The output always gets bigger. This is in contrast to a non-decreasing function, which encapsulates also the increasing functions. This is where the function is allowed to have it where if you have the input n and then you have the input n plus 1 and you feed these into the function, each respectively, it has to be that whatever the value is for n, as the output of the function, it has to be at least whatever is coming after it. So it means that it's allowed to plateau like this and remain flat. But it's allowed to, it could go either up or it could be plateauing like this. It could flatten out. Those are kind of the two stipulations when you see a non-decreasing function like this. Now, the third kind, and this definition applies here, actually encapsulates all of these other two. It's called eventually non-decreasing. This simply means that the function's allowed to wiggle around, kind of like me wiggling like this. I'm allowed to have it where it's neither increasing nor non-decreasing up to some point, and that point n0 either here or any point after this. As long as it exists, it behaves like a non-decreasing function. So that's what I mean by an eventually non-decreasing function. That's also why I said it's also called an asymptotically non-decreasing function. You may notice that this n0 is very similar to the definition of big O. That's not a coincidence. So, that being said, are there any questions about this definition? The thing I'll tell you up front is that almost every function you're going to play around with that you analyze from a complexity standpoint will most certainly be one of these eventually non-decreasing functions. But you have to be very careful because sometimes you're given a function, it doesn't satisfy that property. And you might ask, how would you check this? One standard way of doing this is by proof via mathematical induction. So that's one way you can accomplish such a feat. But all the kind of friendly functions that you're familiar with, all are eventually non-decreasing. So like constant functions, logarithmic functions, polynomials, these are all are eventually non-decreasing functions. So that's the first thing I want you to be aware of, is this idea of an eventually non-decreasing function. The second one is this idea of a smooth function. Now I must stress that some people have different definitions for what a smooth function is. This is the one that's often used in algorithm analysis. So what it simply is I give you a function. And it satisfies two properties. The first property is that it's eventually non-decreasing. The second property is that f, when I give as input 2 times the value of the initial input, like if it's 2 times n as the input I give into the function, it has to be that it's big theta of f. So it's f of 2n, where I give it twice as much of the input, has to be that it's big theta of f. So this is what concept of smooth is. So that's what a smooth function is. It has these two criteria. So the way you would establish the second criteria is you just imagine you're just proving a claim involving big theta, except instead on the left-hand side, you just write whatever f is, where everywhere where you had an n, you would replace it with 2n. That's it. So you might ask, okay, so what kind of functions are so-called smooth? Well, constant functions are, log base 2 of n is, polynomials, like if I give you n to the power of k for any one constant k greater or equal to 0, these are all smooth functions. It's also really nice that a lot of the functions that we tend to work with are smooth. At least many of the ones that we've seen so far. Now, there are ones that are not smooth, however. For example, 2 to the power of n is not a smooth function. So just be very mindful of the fact that not every function is smooth. There's actually really nice consequences for functions that are smooth, which I want to talk about. But I thought I would do a quick example just to show you how you could prove that second criteria here. So let me do that with you, okay? So before I proceed, does everybody understand the definitions of these two concepts? Eventually non-decreasing and smooth. Because I'll do an example showing you how we can establish that a function is smooth. And I'll do it actually a little bit faster because I'm going to show you how I can apply that limit theorem I gave you much earlier on in the course. I'm going to just employ it to do this a little bit faster. So let's head on over here. Let's head over here. So I'm going to do a quick example just to show you how you can use this limit theorem that I gave you way back earlier in the course. So keep in mind, I could also have proved this using the definition of big theta, which we've been normally doing, but I feel like I want to show you at least some usage of the limit theorem that I gave you earlier on. So let's do a quick example. So I want to establish to you that log base 2 of n is smooth. Now I told you up front that it is eventually non-decreasing, so I'm not going to worry about that. The reason why the logarithmic function is eventually non-decreasing is in fact an increasing function. So by definition, it has to be eventually non-decreasing. So let's do an example. I'm just going to check this. So I'm going to try. So let's try proving that log base 2 of 2n is big theta of log base 2 of n. So I'm going to do this with the limit theorem for big theta that I gave you earlier. So I'll just, for abbreviation purposes, I'll just call it the limit theorem. I know in calculus that is something else, but it's just an abbreviation for, we talked about it earlier on in the course. Remember, I gave you that theorem that had all those nice consequences if I employ a limit with a quotient between two functions, and whatever the limit spits out, if it exists, it will tell me what asymptotic relationship the two functions have. So this one's great. So I'm just gonna applying the property. We're gonna do the limit as n approaches infinity. So I'm gonna be kind of loose with this. So the limit as n approaches infinity of log base 2 of 2n. So the first function goes right here. The second one, the one inside of here, goes right there. Log base 2 of n. Now, because the great thing is that this is log base 2 of 2n, right? I can employ the product property of the logarithm. So I could just simply split this logarithmic term on the top into 2, right? So I end up with log base 2 of 2 plus log base 2 of n. And what's log base 2 of 2? It's 1, exactly. It's just 1. So I just have 1 plus log base 2 of n over log base 2 of n. And now, the great thing about this is that, well, I'm just going to rewrite this to make this a little easier to see what the limit would be. So I'm just going to carry through this division here, but I'll have the 1 over log base 2 of n separately. So I'm just carrying through what this would be. And notice that it's just 1 plus something. And what does 1 over log base 2 of n, what does this become as n approaches infinity? Remember, log base 2 of n is an increasing function. 0, exactly. This part here, that approaches 0, and I just have 1 plus 0, at least when it comes to the limit, and that's equal to 1, right? So you thought that calculus would just go away. It's very useful sometimes. Since 0 is less than 1 is less than infinity, by the limit theorem, log base 2 of 2n is big theta of log base 2 of n. And since I already told you that logarithmic functions are eventually non-decreasing because they're increasing functions, this would actually be sufficient for a proof to say that log base 2 of n is a smooth function. So are there any questions at all before I kind of pull out another fun theorem at you? And I'm going to show you this theorem because it's a really neat one. It's a little bit lesser known, but I want to show you it because it actually gives you some really nice analytical techniques you can use to simplify down analyses. And you may have seen this idea subtly used in maybe possibly earlier courses. If not, you may encounter somebody one of these days being like, oh, assume n is a power of 2, and they do that in their analysis, and they never explain why they're allowed to do this. I want to show you how and where that comes from. So this is something that isn't just about recursive algorithms. It's a concept that is very helpful that you'll run into at some weird point, possibly. But yeah, so if we're okay with this example, give me 2 thumbs up, everybody. Okay, now wonderful, wonderful, wonderful. I'm seeing the thumbs up. It feeds me, it feeds me. So anyways, here's a theorem. It's often called the smoothness rule. So here it is. Here it is. It's going to be a little bit wordy, but the idea behind it is very simple but effective. So for those that really don't like having to round up and down numbers and things like that, the smoothness rule is your best friend when it comes to proving asymptotic claims. So things about big theta or big O and so on. This allows you to, I wouldn't use the word cut corners, but most certainly it theoretically gives you the grounds to cut the corners based on the properties of the functions themselves, which is wonderful. So it isn't really cutting corners, it's just that I'm allowed to make simpler assumptions and I can get away with it. So let there be two complexity functions. Two complexity functions, f and g, where f is big theta of g, when n is a power of an integer constant, b greater than or equal to, I believe it's 2. I just want to make sure I get it right. Greater or equal to 2. Yeah, that's what I thought. I just want to make sure because it's so integer constant b greater or equal to 2. And we have the following. So now this is the statement of the theorem. This is the setup. So I know that f is big theta of g when I make the presumption that n is a power of b. That's what I'm doing here. So for example, what I'm saying is suppose I made some simplifying assumptions in my analysis and I said, okay, I'm going to assume that n is a power of 2. This oftentimes makes it easier to perform calculations in my analysis. Sometimes this, every once in a while, in a blue moon, becomes helpful to do. So here's the statement of the smoothness rule. So if f is eventually non-decreasing, and g is smooth, then f is big theta of g unconditionally. So let me just reiterate this. So let there be two complexity functions f and g, where f is big theta of g. When h is a power of an integer constant b, so I'm going to make this presumption, and then I say if f is eventually non-decreasing and g is smooth, then f is big theta of g unconditionally. So that means that it is regardless of this assumption I made here. So for example, if I knew these two conditions are satisfied, like f is eventually non-decreasing and g is smooth, if I were doing this analysis where I established that f is big theta of g, and I assumed that n was a power of 2, for example, I can get away for free, based on the smoothness rule, that f is big theta of g for every n. So this is a very useful theorem in the sense that if you ever find yourself in a predicament where it's a little bit hard to round up and down numbers and it gets very tedious, you can make some assumptions about the input n, and if these two functions have these two properties here, one that's eventually non-decreasing, the other one's smooth, which, by the way, g has to be eventually non-decreasing as well by definition, then that means that you could just simply, whatever you assume up here, it's allowed to, it still will hold regardless by the smoothness rule. So are there any questions about this theorem? So I'll give you one quick example. I'll just say it out loud. There is a statement of this actually in the notes if you want to see how it gets invoked sometimes. But one example of this you may run into quite often is sometimes people will presume that the input, or say for example, oh, the number of elements in an array is a power of 2. This is something that somebody might do, for example, if they're analyzing something like binary search. This ensures that always the numbers, when you divide them by 2, they always break into 2 even halves, for example. It's very similar with algorithms like merge sort, where the halves will end up being of equal size if n is a power of 2. So if you make assumptions like this, and you know up front that your function is smooth, so the one that your outcome or result is based off of, in the case binary search, it's log base 2 of n, right? We know that's smooth. Then you can just invoke the smoothness rule. The smoothness rule. I was about to say smallness rule. I can invoke the smoothness rule, and I can just clean up the entire thing and still get my result. So it's something I like to show just so that you can see that it's a useful tool if you find yourself dealing with things that aren't very easy to cleanly divide in pieces. And this will come up when we start looking at a couple neat theorems a little bit later on. So I just want you to be aware that there's a way I can actually simplify down analyses just by making a simple presumption like this, assuming that f and g have these properties. It will come up later. So if not today, it will come up on Tuesday. So anyways, if there aren't any questions about this, I'm going to proceed to start talking about recursion trees. So let's head on over here. Let's go this way. So the smoothest rule lets you be, I guess the best way, the funniest way I could describe it to you is it is correct but sloppy thinking. So like you can make sloppier assumptions and you're allowed to make them, and it's perfectly safe to do so. That's what the smoothest rule basically gets you to get, which is wonderful. So anyways, let's talk about recursion trees. Okay. So oftentimes, when you've done possibly this in the past, maybe in 210, when you look at a recursive algorithm, usually the strategy is that you come up with a complexity function that measures the running time, right? The number of operations that happen, for example, in the worst case. This is something that we've done before. But often when we do this, it sometimes isn't very clear how we came about it. So often we make a guess once we have our idea of a recurrence relation, we would like to know what the big theta result is, or if we're thinking about big O, just big O. So often when we look at a recurrence relation, we employ techniques that often are based on our ability to see patterns. So you may have seen something like this, for example, in 210, with so-called iterative or repeated substitution, possibly. So this is going to be very much the same idea, but it's going to be, like I said, the same thing, but less, which is great. Often, when devising recurrence relations, for the running times that M looks like it just got a byte read out of it. Running times of recursive or divide and conquer algorithms we usually do the following, right? First, I'm just going to give the abridged version of these. I have much more complicated explanations in the notes. First thing we did, and this is just what I said just a moment ago, we derive a recurrence relation. So the way we did this very often is first we ignore the recursion right? We first started off by often we would ignore the recursion and then count all the non-recursive work, right? Recursive work. So this is very often what we would do if we were trying to analyze a recursive algorithm, right? So something that we very often do when we derive a recurrence relation based on this. And then we can do some nice analysis and we usually simplify it down. Sometimes it's very straightforward how we would do this, such as the example where we were looking at trees, it's very much where you don't have to walk through this much more complicated process. You could just invoke properties of the trees themselves. And then, of course, after this, when you do this, then you incorporate the recursion, right? That's how we came up with if you come up with a recurrence relation, you need to know how many recursive calls are happening and how big they are. Are they of equal size? Like the subproblems that you're solving, are they of equal size or do they differ in size? This is a big part of this process, right? Where you count up how many recursive calls can happen. So, naturally, once you have the recurrence relation, we try to figure out a closed form. We figure out a closed form, right? So this is very often what some people would refer to as a guess. I don't really like the word guess, but it is kind of what you do if you have a recurrence relation. You're trying to usually figure out what the pattern is, and then you usually invoke properties to come up with an estimation or an actual value for whatever that recurrence relation would give for an arbitrary input. So you figure out a closed form. In the past, you may have done this through repeated substitution or so-called iterative substitution, possibly. If not, earlier in the course, we did some things kind of like this, too. So, of course, there's sort of a check phase to this process. Now, I'm not going to focus so much on that. But there's a check to verify. Usually this is done with induction. So I will have an example in the notes showing you how you might do this in one of my examples when I do the recursion tree. So if you want to see an example how you might do mathematical induction to check your guess, I'll have an example in the notes. I mostly have to do that because I have no guarantee that everybody knows induction coming into this class. Anyways, the last thing, of course, is to determine the asymptotic behavior. So this is, of course, where I determine. So determine the asymptotic behavior. So this is, of course, figuring out like the big theta, for example, or big O, or big omega. Right, this is a typical process for analyzing a recursive algorithm, right? That we typically go through this process in some way, shape, or form. Usually verifying, in our case, when we see some like tree or graph-based algorithms, we usually invoke some property that the graph had, as opposed to using induction. So what I want to do is I want to walk through this process of how you might think about a recursion tree. So you might ask, Dan, why would we use this idea if I have this repeated substitution thing? It will help you make good guesses. So I'll just mention that recursion trees help make, I'll put in quotation marks, good. It's not really a objective term. Help make good guesses. Because it's intuitive to what we would normally think of as a call tree in a recursive algorithm. So you know, when I call recursively an algorithm, each of these creates an activation record that goes on the call stack, right? But you could also think of it, if I have multiple recursive calls, you could imagine it like a tree where I have my initial call, then I have all my recursive calls that happen, right? Well, the recursion tree method allows you to visualize the recursion like this, and we also could come up with a pattern based on this idea. So it's very intuitive for computer science folk. So that's why I like to show it. So you don't have to think very, I don't know, the best way I could describe it is you could be very analytical with this technique, but most certainly it makes it a little bit easier to visualize what's going on. So I'm going to do an example just to kind of give you a flavor for this. So I'll do a couple of examples. And I'm hoping that you'll see the parallels between this and iterative substitution. So the first example I would like to do is consider factorial. That's probably one of the first few kind of examples you may have seen of recursion, right? Learning how to compute factorial. If not, we're going to do it here. So let's consider factorial. So let's consider n factorial given any positive integer. So I'm just going to define it on positive integers just for the sake of simplicity here. For given any positive integer n, and factorial is going to be equal to n times n minus 1 times n minus 2 all the way down to 1. For those that are kind of the combinatorics fans in the room, you might know 0 factorial is equal to 1, but I'm not going to focus on that here. So you might think about how we might compute factorial recursively. Well, very naturally, if I think of factorial as a function, where I give you n as its input, well, think about it. Think about it. Well, suppose that I give you the idea of, I could write this out recursively, right? So, for example, if I wrote out like this as like a function, like say if I have like I write out as factorial of n, well, factorial of n, you know that this is n times n minus 1 times n minus 2, and so on down to 1, right? But notice that all of this, this is just factorial of n minus 1, right? And I could keep going down this process. So do you see, all I have to do to compute factorial, if I think about it recursively, is I have n times whatever factorial is when I reduce its value for the input by 1. And eventually I'll have it where I have to define what factorial of 1 is, right? So I'll have some base case eventually. So you know right away that so just to kind of put this all together in a nice bow, you can think of this as recursively. So recursively you could think of it as if n is greater than 1, n factorial is equal to n times n minus 1 factorial, right? And when n is equal to 1, then you know 1 factorial is equal to 1. So naturally, I'm going to write out an algorithm that computes factorial, and we'll analyze it, okay? So let's write out some pseudocode for this. So first, before I proceed, is factorial clear to everybody? You probably have seen factorial before. I'm just kind of running us through kind of like the basics, so that way we can kind of connect all these pieces together. So consider fact of n. Input, output, as I described. I'm just keeping this up shorter for us. So if n is greater than 1, then you know right away if that is the case. So this is the recursive case, right? So you can think of recursive algorithms naturally in terms of a recursive case and base cases, or potentially more than one base case. So if n is greater than 1, then you're just going to simply return n times factorial, or fact, of n minus 1, right? And else, otherwise, this is our base case, we just simply return 1. So here's a recursive algorithm for factorial, right? So are there any questions or anything that is unclear about factorial? So why don't we analyze it? And we'll walk through this process here. So remember, when I formulate the recurrence relation, I'm going to first ignore the recursion. So remember, I ignore the recursion, so I'm just going to treat this like it's some constant number of operations when I do the analysis. And then I'm just going to count up all the operations, and so all of the non-recursive work that happens at the algorithm, and then I'm going to incorporate it back in by figuring out how many recursive calls happen, right? And sometimes in more complicated algorithms, sometimes that how I incorporate it isn't trivial. Just like, for example, with some of our graph traversal algorithms, like depth first search, it's technically the way we wrote it was a recursive algorithm, right? But we use properties that we knew about depth first search to determine how many calls were happening. So it's the same idea, it's just on a much smaller scale here. So let's figure out what's going on here. So the recursive case happens whenever n is greater than 1. So that means whenever n is greater than 1, I'm just doing this, right? So now, all I'm going to do now, once I've noticed this, the non-recursive work that happens, I know non-recursive work isn't really an exact term, it's just me counting up all of the operations when I ignore the recursion. That's what I mean by non-recursive work. Yeah, non-recursive work. So the non-recursive work in this case is where, notice that each call does some constant amount of operations, right? So remember, we're ignoring the recursion. I don't know what's going on with this right now, so I'm just going to ignore that for now. But if I look at this algorithm after that, notice even if I counted all the operations, still some constant number of operations, right? So it does this before it attempts to solve a smaller subproblem, right? So that's all that's happening. Each time it's a constant amount of operations, right? So that's the first part, the recursive part. So now we're going to try to incorporate the recursive work. So the recursive part. So let's look at the recursive part. So one thing I want you to notice is that whenever I have n as my input, it always gets decremented down by 1, right? That's what happens every single time. There's only one recursive call. It happens right here. But it always is that n gets decremented down by 1. So n is decremented by 1 and solved for a subproblem, right? So it means that every single time I consider the recursive case, I always have it where I have whatever I have, I'm going to call it recursively with the input being 1 less. And on each one of these calls, I do some constant number of operations, right? So this happens whenever n is greater than 1. How many operations happen when n is equal to 1? Could somebody tell me? So when n is equal to 1, you know it's going to check this obviously, but it doesn't go into this if statement. Instead it goes to the else, and it just simply returns 1. If I were to tell you in terms of functions, how many operations does it do? Is it like a linear number? Is it a constant number? Is it exponential? Oh boy, that would be terrible if this was exponential. but what kind? How many operations happen in the base case? Is it exponential? Is it linear? Is it constant number of operations? It's constant, exactly. Exactly. So we know that this is what occurs when n is greater than 1. So when n is equal to 1, a constant number of operations occur. So I'm going to take all these bits and pieces that I've derived, and I'm going to formulate a recurrence relation with this information. So notice that when n is greater than 1, what happens? So I'm going to come up with a complexity function that's going to represent the running time of this algorithm. So it means that if I write it out, so this would be what the complexity function might look like. So if I say t of n, where n is our input here, like the input, the size of the input. So if I have t of n, then t of n is equal to t of n minus 1 plus 1. If you think of the constant number of operations as just, in terms of being like big theta, it's just 1, right? Like I could have written another constant right there if I wanted to. It doesn't make any difference. But notice that when n is greater or equal to 1, this seems to reflect what I just described over here, right? So that's what happens when n is greater than 1. And we know that when t of 1, we know some constant number of operations happen there. So notice that by going through this process, I've formulated a recurrence relation based on the running time of the algorithm. So did my analysis. This is now representing, asymptotically speaking, the number of operations of the algorithm in the worst case. So like I said, you could easily just replace, say if you really don't like that, I put a 1 here. It's okay. You could call it like C1, for example. If you want to call this C2, you could call it C2. That's okay too. So I just wanted to show you how I could go through this thought process of deriving a recurrence relation that represents the running time of the algorithm. Are there any questions for how I came up with this recurrence relation? Okay, so if there aren't any questions, I'm going to proceed now to try to go through the steps that we have. So far I have derived the recurrence relation. Now next, what I need to do is I'm going to try to I'm trying to figure out what's going on here. Now, the great thing about this recurrence relation is it's very simple. It's very simple to figure out what's happening here. Every single time I have the input, I decrement the input by 1, and I apply the function again. But every time I do this, I add 1 to whatever the value would be for a given value of n. So it happens every single time. So what I'm going to do is I'm going to first just show you how I would approach this using iterative or repeated substitution. So putting this together, I'm going to show you kind of 2 ways you could look at this, so that you can see that really I'm just going to be describing, when I talk about the recursion tree, it's just another way of looking at what we were doing before. So I'm going to look at iterative substitution. So just for the sake of simplicity, I'm not going to write a full paragraph as saying, oh, let's derive the worst case time complexity. I'm just going to go through and just get right to the analysis, okay? So I'm going to do iterative substitution on this side, and I'm going to show you how I do it with a recursion tree on the right side. So I'm hoping you'll see that there's a lot of similarities going on here. So what I'm going to do is I'm going to keep repeatedly writing out the definition of the recurrence relation based on a pattern I'm observing here. And it's the one I just described. So you know that t of n is equal to t of n minus 1 plus 1. But this is equal to, so I'm just going to take this and plop its definition in and see what kind of pattern we get happening here. Well, t of n minus 1 is equal to t of n minus 2 plus 1, right? Well, what is this? So now notice that it's 1 here, then I have a 1 here. Well, suppose that I just kind of lump these 2 together. You know, it's plus 2, right? So if I apply the definition of t of 2, well, what happens? It ends up being t of n minus 3 plus 1. And I'm just going to take whatever I had here. I'm just going to simplify this down. So now notice if I were to add 1 and 2 here, I get 3, right? So you'll notice that eventually, if I just keep doing this over and over again, notice that every single time, when I consider t of n minus 2, it's 2. When I have t of n minus 3, when I write this right here, it's 3. So what's going to happen when I eventually get down to t of 2? I'm going to end up with t of 2 plus 1 plus n minus 3. And eventually I'm going to have it where it's t of 1 is plus 1 plus n minus 2. So I'm just collecting up like a bucket all of the ones. Note that if this was a little bit more sophisticated recurrence relation, I would have to figure out, probably have to write out a sequence of equations to do backward substitution backwards up. So I'd start at t of 1, then I would plug that into t of 2, then I plug t of 2 into t of 3, and so on. This recurrence relation is very simple for me to do this. It's because I know what the pattern's going to look like. It's very simple. But now, if you notice, t of 1 is just 1, right? So I have 1 plus n minus 2, which that's just equal to n, right? But we know right away that that's big theta of n. So that's exactly what you would expect, that fact takes big theta n time, right? That's exactly what you'd expect. Now, I'm going to do this using the recursion tree method. So I'm going to show you another way I could visualize this. So recursion tree. And the reason why I like to show the recursion tree is because, one, we know a lot about trees, right? So I'm going to use a lot of properties of trees to make this a little easier. Because we've seen that when we studied trees, there's a lot of lovely properties they had, and it made the analysis a little bit easier. So I'm going to try to capture this idea. So when I go through and I start off at t of n, so suppose I have t of n, which I'm going to replace this, by the way, with in a little bit here. So I'm going to imagine for my recursion tree, I have the level in the recursion tree is going to correspond to how many recursive invocations have occurred. So I'm going to start off at level 0. So this says level. At level 0. And I'm going to have a column called work done. So when I do t of n, well, it's t of n minus 1. So I do one recursive call where I reduce its size down by 1, right? Then I add 1. Well, then the work done is the non-recursive work. So 1 of what non-recursive work happens. So at this given spot, I got to replace that with the amount of work, just for the sake of our discussion here, so that you can see the pattern going on here. Next, what happens when I call t of n minus 1? Well, it calls t of n minus 2, right? So for t of n minus 1, it calls t of n minus 2, which is one recursive call. So we know it's going to be another one right here. It does one for the non-recursive work, which I'm going to reflect in the tree as just a 1. So all I'm doing is I'm going to have it where I have each one of these as nodes in the tree. That's going to reflect the size, so the function invocation at that given size. Usually they put the non-recursive work in there for that given size. Or it could just simply be the input itself. You'll see in a couple of my examples where it makes more convenient to write it one way or the other way. But I'm just going to keep track of how much work gets done at each one of the recursive invocations. So when I have level 2, well, this would be when t of n minus 2 happens. The amount of non-recursive work that happens is 1. And I call t of n minus 3, right? So I call t minus 3. The amount of non-recursive work that happens here is 1. So notice here that I could have easily just wrote, to make this a little easier for you to see, if you really just don't like the 1s being here, you can always write n. That's the size of the input. This is the size of the input. This is the size of the input. This is the size of the input. But notice for each one of them, I do only 1 each time. I contribute 1 each time. So I have a question for you. If you imagine this as a chain, just a straight up chain that goes from the top to the bottom, you know that eventually I'm going to hit 1, right? But the point is that there's going to be some point where I consider any one level in this tree that represents the amount of work that's happening with my algorithm, the number of operations at each one of the calls. If I look at an arbitrary level in the tree, it's just 1. So the guess I'm making is that every time I make one of these recursive calls, it's some constant number of operations each time. So the question I have for you is, how many levels are there in this tree? So how many levels are there? So the question is, how many levels there are for this tree? So remember that the number of levels is always 1 higher than the height of the tree. So remember that the number of levels is equal to the height of the tree plus 1. So how many levels are there? If I keep going through this process. Because you know eventually I'm going to hit it when the input is just 1, right? Well, it's very close. It's very close. So when it's, so remember, I'm looking for when t of 1 happens. T of 1. So think of it like n all, so notice it goes n, n minus 1, n minus 2, n minus 3. Eventually it's going to go down to a point where it's going to be where the input is 1 here. So think about it as 1, 2, 3, 4, 5, 6, 7, 8, all the way up to n. So you're very close, very close. So remember, we're not going down to t of 0, we're going to t of 1. It is just n. It's just n. So the number of levels in the tree, I would normally write this right here, but I got them side by side here. So notice that all I'm doing is I'm almost effectively simulating out the recursive algorithm where I have one recursive call that happens. I tell you how big that size of that input is, and I can tell you how much non-recursive work happens at that level. And I do this all the way down. So this is just each one of these edges in the tree corresponds to a recursive call that happens. If there were 2 recursive calls, then I would have exactly 2 children in the tree. Here I just have 1. Just like if I had 3 recursive calls, you know that you're going to have it where there's going to have 3 children. So I have a very simple question for you. How do I determine the total number of operations? Does anybody see anything interesting going on in that rightmost column over there? So that rightmost column has 1s in it, but the thing is, notice that all I'm doing is I'm accumulating, like I'm collecting up in a bucket at each one of the levels, the amount of work happening at each level of the tree. So what could I do with each one of those numbers I have on the rightmost side? And that rightmost column, the one called work done. So how can I figure out the number of operations that happen for the algorithm using that information? So I'll give you a hint. Remember, just imagine it just like I'm doing the iterative substitution here. Each time I make the recursive call, each one of these, it introduces 1 every single time. You sum them together, exactly. That's how simple it is. You just add up all of the work done at each level of the tree. You know how many levels there are. So you just sum up over all the levels. You know exactly how many there are, right? So now let's put it all together. So let me just summarize it over here. Let's go over here. Let's put it all together now. Okay, so let's put this all together now. So since the number of levels is n, in fact, I'll say that we'll say that the number of levels is n, but remember the height is n minus 1. Then to compute the total work, which is the number of operations that happen at most, simply sum over all the levels in the tree. So this one's unfortunately a little bit simple. So I'm just going to take each one of the levels. Notice the indexing for the level starts at 0, so it goes from 0 up to n minus 1, right? So I'll say that the worst case time complexity. So actually, I'll just write it out like this. So the sum from I is equal to 0 to n minus 1. At each one of the levels, I do one operation each time, right? Some constant number of operations. Well, I'm just going to apply the closed form that you know about. N minus 1 minus 0 plus 1, which is just n, which you know as big theta of n. And it matches up. It matches up actually exactly with what we did over here. So these are just two mirror images of the same thing. It's just now we're using the properties of trees to help us guess the pattern easier. So you're going to notice that the recursion tree method is rather effective when we have several recursive calls that happen, which oftentimes the iterative substitution approach tends to get a little bit trickier to do. So first, are there any questions for how I got this result here before I proceed? So while I wait for a question, if there's any questions, I'm going to have actually at least a few examples here in the notes, because I want you to really see this technique. I want to convince you of it. There's going to be an example in the notes for quicksort. So it's something similar to quicksort. So it's going to be similar to quicksort. You pick a bad pivot in the worst case. So recall in the worst case of quicksort, the idea is that, okay, when you do this partitioning process, you end up with a pivot where you have nothing on one side of the two buckets, then you have all the other elements in the other one. It ends up actually having, if you drew its recursion tree out, it'll be exactly like the one I drew over there, except with every one where I had 1, it'll be n. So it'll be n with respect to the input, so it'll be n, n minus 1, n minus 2, n minus 3, n minus 4, down. But if you sum up over all the levels, you end up with a quadratic. So you'll see that it's a very effective way of visualizing this process. So that example is very similar to the one we just talked about here. So I want to switch gears to another example that is a little bit trickier, because I think it's important that you see a tricky one. Because I do actually have another example that shows you what happens when you select the good pivot. So the one that is always the median. So there's another example that's actually the last example that's in the notes that actually shows you with quicksort what happens when you pick the good pivot, the perfect pivot, the one that's in the median position. So the median, when you pick that every single time. And I show you how you can apply smoothness there to simplify down the analysis. So with that being said, I'm going to use the last bit of today's class to talk actually about one more example. It's a little bit trickier. So I want to walk you through the process just quickly. Just remember with the recursion tree method is we want to think about this as a process where you draw the tree out, then you figure out what exactly is happening at each level of this tree. So figure out how much work is being done at each level of the tree. So focus mostly on that and figuring out a pattern per level of the tree. So draw the recursion tree. Then from there, figure out the total number of levels of the tree. So usually the easiest way to do this is figure out what the height is. And then of course, figure out what the cost is at the last level, because sometimes when we have these trees, they start growing very wide at the bottom sometimes, so that the number of leaves the tree has actually could have a very heavy influence on the running time of the algorithm. So just like when I figured out what the last level was just a constant, you may have it actually be something that's a little bit bigger when it comes to the number of leaves. We just had one leaf in our tree. There can be many, many leaves. And then once you have this, you just sum over all the levels. You end up with a closed form, and then you simplify. Just like I have here. It's really, really intuitive. I like it. I like showing you this because it gives you another way of looking at repeated substitution that's very intuitive to the mind of somebody that thinks about recursion. So let's do another example. So here's a little bit more of a complicated one. So consider where if t of n is equal to 3t n over 2 plus n squared, where n is greater or equal to 2 is a power of 2. So this is one way this power business it sort of appears when we start thinking about recurrence relations. And we're going to say that t of 1 is equal to 1. So the first thing I need to do is draw the recursion tree based on what I described. So let's head over here. I'm going to try to figure out what the pattern might look like when I draw it out like a recursion tree. So let's figure out what the value of the input is for each level of the tree and how it gets influenced here. I warn you, you're going to need a little bit of space for this tree, okay? In fact, I'm actually kind of tempted to write it right here. It's kind of big, but I will draw it actually. Let's draw it over here. I can make it work. It will start getting kind of fat. It gets kind of fat. And I must stress that it's a technical term. So let me proceed. So first, let us draw the recursion tree. So that's the first thing I'm going to do. So I'm going to have the levels on the leftmost side. I'm going to draw the tree in the middle, and on the rightmost side, I'm going to have the work done. So work done. My apologies. Work done. So I'm just going to go through this process. Now, if you recall the recurrence relation over there, how many recursive, if you think about it as a recursive algorithm, which is very intuitive for us to think of, if I had a given node in the tree, how many children should it have? Just think of it like a call tree. That makes it easier to think about. So how many children would it have in the tree? So remember, in our first example, I had one recursive call, so I had exactly one child each time. So how many children will I have this time? Is it 1? Is it 5? Is it 8? What is it? So I'll start off by showing you the root. It's 3. It's going to be 3. So I'm going to write down what the non-recursive work is for the given value of the input. So I'm just going to write it out this way because I think it's a little bit easier to see what's happening. You'll find in my examples I do it this way because it's a little bit easier for me to keep track of the levels, because here's the thing. So I showed you how I wrote down the input each time. I usually like to write out what the non-recursive work is each time, because what you're going to end up doing when you do this is you're going to sum over each one of the siblings, sorry, not the siblings, all the nodes on the same level, and that's what you're going to write on the rightmost side. So that's why I write it out. So you see the first way I wrote it where I had like the ones each time? That's what I'm going to do here, and that's what I recommend you try doing. Because I'm just going to sum over all the levels. So for example, let me write work done a little bit higher up. Tempted to write word, work done. So on the first level, level 0, I do n squared, many operations. Then I have 3 recursive calls. Each one will half the size of the non-recursive work that happens. So I have n over 2 squared for each one of these. So I have 3 recursive calls happen. That's why I have 3 children. What I'm going to do is I'm going to just sum over all of these, and that's what I'm going to write right here. So I sum over all of the nodes on that level, because these are all the recursive calls that happen on the first recursive call. So each one of these will have recursive calls that happen as well. So after 2 invocations of recursive calls, that'll be the next level. So notice I have 3 of these, so I have 3 times n over 2 squared, which this, I'm going to write it, actually, let's leave it like this, and we'll figure out what's going on here. So for each one of these, at level 2, I'm going to have 3 children for each one of these. I'm going to have n over 4 squared, n over 4 squared, because remember, all I'm doing is dividing by 2 each time for my recursive call. So I'm just writing out each one of these. If I went down another level, you might have a lot more nodes. So how many do I have here? I have 9 of these. So I have 9. Each one is size of n over, so the amount of non-recursive work that happens at this call is n over 4 squared. So I have 9 of those, and this is what I have so far. And now, if I were to have each one of these, each of these would have 3 recursive calls that happen. Does anybody see a pattern that's going on here? There's a couple of things. How quickly are we getting children? Is it growing linearly? Is it growing exponentially? Is it growing? Actually, there might be even more accurate term here. It starts with a G. How fast is this growing? Is it growing just like a chain? It's splaying out a lot, like geometrically. That's exactly the word I'm looking for. It's growing geometrically. So you're going to see that it's going to play a very important role on how we try to figure out the pattern. So I want to look at an arbitrary level I of this tree. There's going to be many, many children as this goes down, but I want to figure out a pattern at each one of the levels so that I have this is where I'm doing my guess. So this would be something I can check using mathematical induction afterwards, if I would like to. But usually these guesses are really good. Subjective term. Anyways, so I have 3 over 2. I square this. One thing I want you to notice is I could rewrite this right here. I could rewrite this as 3/4 times n squared. And then this right here, I have 9 times n over 4 squared here. Now if I square 4 here, that's 16, right? That's 16. What's 9 over 16 when I simplify it as a fraction? What is that? What's 9 over 16 if I simplify it down? It's 3/4. I was about to say 3 squared. No, it's 3/4. But notice that this is just 9 here, right? So notice that I can rewrite this instead. So notice I have imagine this as 3 squared, and this is 4 squared, right? So imagine this as 3/4 squared times n squared. So I'm trying to find a pattern. So this is usually the toughest part of doing this whole process. So I go through this process, but notice that each time, if I look at each of the levels, this is what I want you to notice. Look at each on the levels. I'm going to try to figure out a general form for the amount of non-recursive work happening at each level. So remember, I'm summing over each one of these, and the goal is to figure out what's happening at an arbitrary level. So if I sum over all of the levels, I can figure out the total amount of operations that happen for the algorithm, and I come up with a general form. So notice that I can rewrite this actually as 3/4 raised to the power of 0 times n squared. This is 3/4 to the power 1. This is 3/4 squared n. For arbitrary level, I could rewrite, so my guess is that this is 3/4 raised to the power of I times n squared. That's my guess. So this is the guess I have here. So eventually this is going to get down to a whole bunch of t of 1s potentially if n is big enough. So if n is big, you're going to end up with a whole bunch of t of 1s eventually. Eventually there's going to be a whole bunch of t of 1s all the way down here as leaves. And I'll tell you how much non-recursive work is happening. So all these would just be a whole bunch of 1s. So one thing I'll tell you up front is if I wanted to know how many leaves there are, I could apply this pattern. Or I can think about it using the definition of a logarithm, because the number of levels in this tree, notice every single time I do this, I half the size of the input, right? And you know that means that it's going to be something it's going to be logarithmic, like the number of levels. You could formulate this because n is a power of 2 as log base 2 of n plus 1. So the question is, okay, so how many could this go down? Well, I can think of it how many times it's going to take me to get down to eventually this t of 1. One way I can write this out is that the number of leaves that I have at the bottom here is going to end up being big theta of n to the power of log base 2 of 3. This comes from the definition of a logarithm. So you might ask, okay, so what do we do with this? So I'm going to quickly write out what the formula is, and then I'll let you take a look in the notes how I simplify it down. This one's a little bit more complicated for its analysis, but I want to quickly just finish off the example we have here. We got a minute. Actually, a little bit less than that. So I'm going to go a little bit fast here. I just want to write down what we need to do, because remember, I have to sum over all the levels. So Dan's going to boogie as fast as he can here. I just about lost my little bird friend. So anyways, what we're going to, so if I sum over all the levels, so I'm going to sum up over all the levels, then we get the following. So t of n is going to be equal to 3/4 to the power of 0 times n squared plus 3/4 to the power of 1 times n squared plus all the way until the number of levels minus 1. Actually, I'm going to minus it off 2 because I account for the number of leaves in here. But if you were to have this where you're going through all of them all the way down to the leaves, you'd commit yourself to all the way down to all the levels, like my first example. So I'm just going to write this way because it makes it a little easier to formulate it. 3/4 to the power of log base 2 of n minus 1. So this is just, it's not the level all the way, it's not the furthermost down one. It's not the one with the leaves. It's just the one just above that, because all the leaves, we know that this is big theta of n to the log base 2 of 3. So if I simplify this, I get a sum. So if I go sum is equal to what, I is equal to 1 to log base 2 of n minus 1. If I write this out, I'm just going to write this out as a summation. And if you go through some steps using the geometric series, so there is some more steps here. I want you to take a look in the notes for how I did this. It's not a simple analysis, by the way. But eventually you'll get it down to this being big O of n squared. So one thing I want you to note is that the way this recursion tree plays out, it alters based on how many leaves you have versus how much work is happening at the root. There's going to be a trade-off that's going to happen between them. In this case, you'll notice that the amount of work that's happening at each time grows geometrically. So as we work our way down the tree, the number of leaves grows. But it doesn't grow fast enough so that when the amount of work comes into play, it's really just the amount of work that really seems to take all the work. But you're going to see that, and I'll make a note of this. I want you to take a quick peek at it. It's just below the analysis here, where I break out these 3 cases. So where the amount of work that happens heavily at the root, and then the amount of work that happens at each level dwindles down. Or it happens that many, many leaves happen, and the work seems to go up. But because there's lots and lots of recursive calls happening. Or it could be that at each level of the tree, the amount of work that happens at each level seems to even out. The example I'm going to refer you to in the notes is where I have quick sort. So if you consider quick sort with a median pivot, this is an example of the one I'm referring to. So there's another example in the notes where I do quick sort with a median pivot, and I show you how you can use smoothness there to simplify down the analysis. So that being said, I want to say thank you very much, and have yourself a beautiful day. I'll see you later.